Okay, so we're going to talk about the relationship between electrical potential of a cell and Gibbs free energy. So you know delta G is Gibbs free energy, and it is defined as the energy available to do work, and that's exactly what you want a battery or an electrochemical cell to do. Okay, so we have said in the past a couple of things. One is that for a process to be spontaneous, the delta G, if delta G is negative, it is spontaneous. And we've also said that if the cell potential is positive, that the reaction is spontaneous and will go. So we can actually set these equal and say that Gibbs free energy is equal to the negative, and it's negative because Gibbs has to be negative, cell potential has to be positive, so to make them the negative of each other is negative NFE, negative inf, right? Where N is the number of moles of electron in a balanced redox equation. So let's take a look. So if I have Zn 0 going to Zn 2 plus 2 electrons, and copper 2 plus going to, plus 2 electrons going to copper 0, I've lost 2 electrons and gained 2 electrons. You know how sometimes, let's say this is just 1 electron, we've got to multiply this times 2. So whatever that gained and lost number of electrons is your N. So in this case, N equals 2. F is Faraday's constant, and it's the number of coulombs of charge per mole of electron. Okay, so we've used Faraday's constant before, and I think on the AP equation sheet it's 96,500 coulombs. Okay, and we need to use that, and then the cell potential. Okay, so here, if we have a sample problem where we have this reaction and we know that the cell potential is 110 volts, we can determine what Gibbs free energy is by taking N, and here we said N is 2. We have Faraday's number, which is this constant, 96,485, and we can multiply it times the volts, and we know voltage is equal to joules per coulomb. It's a small c. And so if we have 1.1 volts, that's 1.1 joules per coulomb. And you see how nicely things are going to cancel out here. And we can calculate that the Gibbs free energy associated with this electrochemical cell would be negative 212 kilojoules, quite a bit of energy. Negative delta G, which means it is a spontaneous process. Okay? The fact that the cell potential is positive also told us that it was spontaneous. So let's take a look at a couple where we have to determine whether or not they're spontaneous. Alright, so determine whether the following reactions are spontaneous under standard conditions. So let's take a look at A. And in A we have Cu becoming Cu2 plus 2 electrons. And in the bottom we have Cl2 plus 2 electrons becoming C2Cl negative. So we can take our standard reduction potential table, and I have Cu2 plus 2 electrons becomes Cu, which is the opposite of this. The value for this is 0.34 volts, so for this it's going to be negative 0.34 volts. And if I look at Cl2, let me see, it should be at the top. I'm sorry, I have my equations mixed up. I'm mixing up A and B. So this is the first part of A. The second part of A is I have 2H plus 2 electrons becoming H2. And if we look down on the table, we'll find that the value is 0, because if you remember, all the values on the table are compared to this, and this is arbitrarily set as 0. Okay, so if I add those up, I get a negative 0.34 volts, and because E is negative, this is not spontaneous. Alright, so let's look at all of B now. My bad. Alright, so for B I'm going to have Cl2 becomes plus 2 electrons becomes 2Cl minus to make that balance. And I'm going to have 2I negative becomes I2 plus 2 electrons. So gains 2, loses 2, don't have to make an adjustment to the number. Alright, so let's look them up. Cl2 plus 2 electrons is the way it's written here, and that is a value of 1.36 volts positive. And 2I, so on the table it has I2 plus 2 electrons becomes 2I minus, and that value is 0.53. But because we have it in the reverse here, I have to change the sign, so it's negative 0.53 volts. And if I add those up, I get a positive value, something like 0.83 volts. So this, because E is positive, it will be spontaneous. Alright. Okay, in this problem we're going to actually calculate the Gibbs free energy associated with a electrochemical cell. Okay, so here I have copper 2 plus aluminum becoming copper plus aluminum 3. So if we remember, the equation for delta G naught in standard conditions is negative NF E naught. Okay, so I've got to figure out how many electrons are being exchanged first. So I have Cu2 plus 2 electrons becoming Cu. I have aluminum becoming aluminum 3 plus 3 electrons. Okay, so if I look up on my table, Cu2 plus 2 electrons, and make sure you do the one plus 2 electrons because there's lots of Cu versions on here. And I get a plus 0.34 volts. If I look up aluminum, it gives me the reverse, this leading to this, and it tells me the value is negative 1.66. But of course I changed the sign because I've reversed the order of the reaction. So what I get when I do all that is I get, let me just make sure I do the Cu. Let me see, did I do this right? Yeah, okay. And when I add these together I get 10, exactly 2 volts. Okay. So the thing I need to look, that gives me my E, right? Now to find N, if you notice, I've gained 2 electrons, lost 3, so I've got to do this whole thing where I multiply this times 2 and this times 3, so that they both lose and gain 6 electrons. So my N in this case is 6. So my delta G naught is going to be 6 moles of electrons times Faraday's number, which is 96,000. I'm going to use the 500 joules per mole of electrons. You multiply that times my voltage, which is 2 volts, which is 2 joules. My bad, this is coulombs per mole of electrons, so it's 2 joules per 1 coulomb. Cancel coulombs, cancel moles, and if I plug and I chug, I end up with 1,048 kilojoules of energy. Quite a bit. And it's positive, so it is spontaneous. Well, it comes out to be negative. The E0 is positive. If I multiply this times a negative number, I end up with this. It releases that much energy, so it is spontaneous. Okay. Okay, in this section we're going to talk about what happens when we are not at standard concentrations. So let me see, get my marker going. Non-standard concentrations. Because everything we've been doing so far is E naught, right, which assumes standard conditions, and when we're talking about solutions, we're talking about always being at 1 molar. So if we have a case where we are not at 1 molar, we can calculate what the cell potential will be. And this uses what's called the Nernst equation. A guy named Ernest Nernst came up with it. And it allows us to figure out what the cell potential is when it's not standard. You can actually simplify this equation. E naught is these at standard conditions, which we get from the reduction potential table. R is the gas constant that has the energy factor. T is Kelvin, of course. F is Faraday's, that's a constant. So we can actually take R, T, and F, if we're assuming standard conditions, which is 25C or 298, and simplify that down to one number. And if we do that, we get 0.0591 times the log over N, which is the number of electrons that are being exchanged, times the log of Q. Now, if you remember from equilibrium, Q has the same equation as K, but it happens, Q is when things are not at equilibrium, right? So if you remember, Q is the product concentrations raised to their coefficients over the reactant concentrations raised to their coefficients. And this is what Q is. And if Q is equal to 0, it's at equilibrium. Okay? Alright, so let's take a look at how we can apply this. So we want to calculate the electromotive force, which is E when it's not 0, at 298, so it's standard temperature, generated with the following reaction, which has a standard potential of 0.79 volts. Okay, so we're going to use the Nernst equation, which is E is equal to E naught minus 0.0592 volts over N times the log of Q. This might be a good equation to memorize, because there might be some multiple choice questions where you can't use your table. Alright, so we're given the E naught. We can figure out N by looking at the equation and figuring out how many electrons are being exchanged. And if I do that, iodide is one of the things that's being has its oxidation number changed, and it looks like it's going to be by 6 electrons. So we know N is going to be 6. Okay, so we've got to figure out Q. So Q is going to be, here's the equation. So the nice thing about equilibrium constants in Q is that solids and liquids are not part of the equation. So it's really just the aqueous materials, Cr3 plus, if I'm dealing with solutions, otherwise it's the gas pressures, remember that? So the concentration of Cr3 plus raised to the 2 over Cr2O7 raised to the negative, this is a negative 2, but there's no coefficient, so that's nothing, times the concentration of H plus raised to the 14 times the concentration of I minus raised to the 6th. And if I plug my numbers in, concentration of Cr3 is given to me here, it's 1 times 10 to the minus 5. So it's 1 times 10 to the minus 5, and that was squared over my concentration Cr2O7 is 2 molar, and times the concentration of H, which luckily is 1, so it's 1 to the 14th, which of course will be 1, and my concentration of I is also 1. That was nice. That will be raised to the 6th, but will also be 1. So if I take that and I end up with 1 times 10 to the minus 5 squared divided by 2 is all this is. And if I do that, I get 5 times 10 to the minus 11. And if you recall, there are no units when dealing with Q and K. So now I can plug my numbers into my equation, this equation right here, right? So E is equal to E naught, which is 0.79 volts, minus 0.0592 volts over N, in this case is 6, times log of my Q, which is 5 times 10 to the minus 11. And you want to make sure you're able to punch it correctly, but if you do, you end up getting 0.89 volts. Now I can also use the Nernst equation to figure out what my equilibrium constant is, because at equilibrium the forward and the reverse reactions occur at equal rates, and if that is true, then the battery is dead because there's no electrons moving, right? So the cell potential E is going to be 0. So I can use that in my equation. I set the cell potential to be 0, and it's going to be E naught minus this, and I can just simply solve for K. Let's take a look at a sample problem. I have zinc and copper. I plug the numbers into the equation, and I solve for K, and I get a K. That's huge, right? But that's how it works. It's right in the packet. You can follow along. Okay, sometimes we have what's called concentration cells, where we have the same components on both sides of the cell, but there are different concentrations. So in order to figure out what's going to happen to the voltage, we have to look at which side undergoes oxidation and which side undergoes reduction. So we can use our idea of the Chatelier's principle that says if I create a shift, the process is going to move in the direction to get back to that initial concentration. So if I have a higher concentration of zinc ions, let me see, is my pen working? Oops, over here, it is going to naturally move that way. So the Zn2 plus must be increasing in concentration. So the 1 molar is undergoing reduction, right? And the 0.1 molar is undergoing oxidation. We can calculate the cell potential using Nernst, right? Plug in our numbers and we see what we get. It's a small amount of voltage, but it's voltage. Right, we're going to stop there for that.